Okay, so in the previous video we talked about instantaneous speed at a particular moment in time. We talked about the slope of the tangent line at a particular input. Finally, we're going to introduce this notion of what a derivative is. Okay, we're going to define a derivative at a particular point at an input C using two different formulas. The first one you'll recognize from when we did our instantaneous speed. The second one you'll recognize from when we did our slope of the tangent line. These two, in fact, end up being equivalent. So you can use either one. However, it's the second one that we're going to focus on most because it works best with a bunch of different functions, and it also is least confusing once we start to look at the derivative as a function rather than as a real number. Right, so what I want to do is just go through a couple of examples in this video. It should be a pretty quick one, talking about how to find the derivative of a function at a point. And we're going to use one or both of these formulas. Let's start with our first example. We're also going to introduce a little bit of notation here. Suppose we have a function x squared minus 2x minus 1, and we want to know f prime of 2. So what does this notation mean? This is going to be our shorthand notation for any of the following, which happen to be equivalent. The derivative of your function f of x at x equals 2. We also could call this the instantaneous rate of change of your function at the input x equals 2. This also computes the slope of the tangent line to your function at x equals 2. So all of these things are equivalent. And when you're looking through the homework, we could ask about the derivative in any number of ways, talking about the instantaneous rate of change, talking about the slope of the tangent line, or we could expressly say derivative of f of x evaluated at the particular point 2. So to find the derivative of our function at 2, we can use either of the two formulas that were in the previous slide. I'm going to start by using the first formula, the one which more closely matched up with the formula we used to compute the instantaneous speed in the previous video. So what I'm going to look at is the limit as x goes to the point I'm concerned with. I'm going to take the function minus f evaluated at 2 and divide it by x minus 2. Now hopefully what should happen here is when we substitute our function and our function value at 2 into this, we'll do a little simplification and we should be able to evaluate the limit using our factor cancel trick. You can tell right away that this thing we're trying to limit has a domain issue at 2. Right? So if this limit does exist, if we get a real number out of this process, our factor cancel trick should work. Okay, so let's go ahead and plug in our values here. This would be the limit as x goes to 2 of x squared minus 2x minus 1, and our function value at 2, we're going to subtract that. So let's subtract, do a little quick arithmetic. So this would be 2 squared minus 4 minus 1. So we're going to subtract a negative 1 because that's the output of our function at 2. We'll divide this whole thing by x minus 2. And you may start to see the simplification in the top. Right? Specifically, this minus minus, subtracting a negative 1, is really the same thing as adding 1. And when we look at plus 1 minus 1, this whole piece is going to disappear. Now what we can do is factor out a common term in what's left over, specifically of a common term of x. And it leaves us with x times x minus 2 in the numerator, and we still have our x minus 2 in the denominator. So now applying our factor cancel trick at last, the x minus 2, the domain issue with our original limit, disappears, and we're now left with a limit where direct substitution would work. The limit as x goes to 2 of just x. So the slope of our tangent line at x equals 2 ends up equaling 2. The derivative of our function at x equals 2 is 2. The instantaneous rate of change for our function at x equals 2 is 2. Okay, all of these things are equivalent. And the notation we use for this is our f prime of 2. Right? So we can write in our answer, and this completes this problem. Okay, let's revisit this quickly now using our other approach. In this case, we want to limit as h goes to 0, f of 2 plus h minus f of 2 all over h. Now keep in mind, h just means a small little distance that we move away from our input of interest, right? So this gives us the same value as our other formula does. It's just written a little differently. And what we do is we limit that distance goes to 0. In other words, we keep taking inputs closer and closer to each other. All right? Same basic process. We want to use our function value with these inputs, simplify the top, and hopefully what we'll see is an h canceling out of the top and the bottom. So let's get to work. Our first step is to figure out what is our f of 2 plus h. So everywhere we used to see x, we can replace with a parentheses. And then since our input is 2 plus h, we're going to put 2 plus h inside of each one of these parentheses. All right? Keep in mind we're still subtracting f of 2, and when we did our original investigation of this, we found that f of 2 is equal to 1. Okay? We see this whole thing divided by h, and I'm going to start doing a little simplification. Just as we saw last time, the 1's are going to cancel out. Another observation you may see is that each one of these terms have a copy of 2 plus h. So we can do a little factor by grouping here. Pull out a 2 plus h, and this saves us from having to expand. What we're left over with is one copy of 2 plus h. Right? Keep in mind we had 2 copies. We're borrowing one of them, so this leaves us with a 2 plus h. And we'll be subtracting a 2. We're still limiting this as h goes to 0. And we're dividing this by h. And what we'll see is our negative 2 and our positive 2 cancel. So this just leaves us with the limit as h goes to 0 of 2 plus h times the h left over divided by the h in the original denominator. So this is what we wanted. We finally get the cancellation we were looking for, and we're left with our limit as h goes to 0 of this expression 2 plus h. So direct substitution of 0 in for h leaves us with just 2. Same answer as we got in the previous case. I will mention that in some cases, the factor by grouping trick that we applied here will not work, and you really do have to completely expand out this term, and then just see what cancels. All right, so typically in these types of problems, when we use this approach, look for some factor by grouping if you can find it, but there will be cases where you're just going to have to expand out these squares and expand out this multiplication by a constant. Factor everything out, cancel as much as you can, and then look to factor out an h to cancel out of the bottom. Okay, let's do one more quick example. Suppose we're given the function the square root of 10 minus x. We want to know what is the derivative of that function g evaluated at 1. What's the derivative of our function at the input 1, or the instantaneous rate of change in the function g at the input 1. Right, we're going to use our second formula. I want you to get used to this formula because we're going to need it a lot in the next video. We're going to look at the limit as h goes to 1. We look at g of 1 plus h minus g of 1 divided by h. Right? Again, keep in mind, h is just the distance between our original point and the other point we use as our approximation. So we're fixed at 1. We want to move a little distance away from 1. We take a difference of the function values and divide by the difference between those 2 points on the x-axis, which by definition is h. Okay? So what we end up with here is a limit as h goes to 0. And now when we plug in into the top, we'll get the square root of 10 minus our input. Now keep in mind our input here is 1 plus h. Right? So this is just our first term, g of 1 plus h, from which we want to subtract g of 1. Now I'm going to do this a little quicker in my head. G of 1 would substitute a 1 in for x. 10 minus 1 is 9, and the square root of 9 is 3. So I'm just going to put 3 here. Okay? In our next step, we're going to simplify a little bit. And you may have a guess as to what limiting technique we're going to have to employ in order to get our factor cancel trick to work. So we have the square root. Our negative sign is going to distribute through both pieces. So we would have 10 minus 1, which is 9, and then the negative h. So we have the square root of 9 minus h minus 3 all over h. We're looking at a radical, and we can't do direct substitution because we have an h in the bottom. In fact, direct substitution would lead to 0 over 0. So what we need to do is try out our good old-fashioned conjugate trick. So we're going to multiply the top and the bottom by the square root of 9 minus h plus 3. All right? We're going to get a lot of simplification in this numerator term, and we're going to leave the denominator factored. We're not going to expand that out because eventually we'll be able to just do direct substitution on that and we won't have any problems. Okay? So, we've done a couple of examples with this conjugate trick. If you're still uncomfortable with the algebra of how this term up top simplifies, please come see me, please come talk to me about it. It is very important that you know how to do this. But for the purposes of this video, I'm going to gloss over it and just show you how the top simplifies. So we end up with 9 minus h minus 9, and in the top we have h times that conjugate piece, 9 minus h plus 3. Right? As you would hope, 9 and negative 9 cancel. This leaves us with an h and a negative h. So if we pair these off, these are going to cancel to negative 1. Okay? Keep in mind, we had negative h left over in the top, so when we divide by h, you end up with negative 1. Okay? In the bottom, we still have our conjugate term, 9 minus h, plus 3, and we are still limiting this as h goes to 0. So in our last step, all we have to do is substitute our h into our expression and see how it simplifies. So we have a negative 1 in top, and we will have a square root of 9 minus 0 plus 3. This is negative 1 over the square root of 9 plus 3. Square root of 9 is, of course, 3, and 3 plus 3 is 6. So we get a final answer of negative 1/6. Once again, we can go up to the top to our original question. What was g prime of 1, right, which is our notation for the derivative of g of x at x equals 1. This is equal to negative 1 over 6. This is our final answer.